Hi, my name is Kuba Vujciak, and I'm a principal engineer working in AWS messaging, where day to day I take care of simple queue service, simple notification service, and Amazon MQ, all the services that we have for messaging. And today we're going to talk about best practices for serverless queue processing. Let's start with some basics and define what do we mean by serverless. This kind of a new trend of running without physical servers. It's actually more generic than that. When you ask the question what's serverless, we basically try to focus on these four core properties of being serverless. That there's no infrastructure provisioning and no management involved, that the resources you use provide you with automatic scaling, that you end up paying for value, not for idle CPU cycles, and that the solutions provided in the serverless world are designed by AWS teams as highly available and secure, and it's on our plate to make sure that they give our customers the best possible performance and behavior. So let's look at the first of the two serverless services we're going to talk about today, and that is Amazon SQS. It's one of the oldest AWS services that we offer to our customers, and it is a messaging component, a queue to which you can send messages, and the systems that send messages to the queue are typically called message producers. A queue becomes an elastic buffer that can accumulate as many messages as needed. And on the right-hand side on the diagram, you can see that the system receiving messages is called the message consumer, and they get to react to the received messages in whatever way they like. So SQS is special, and it's one of the first serverless services we offered. And it actually fits all of the four properties of a serverless service. It's super easy to create an SQS queue, and the fact that it exists actually doesn't charge you any money. Only when you start using the queue by sending messages to it and receiving messages from it, you will see charges on your bill, and typically fractions of a cent. So it's like the definition of serverless. It's highly available, and it has this very nice property that whatever traffic you're going to send towards an SQS queue, the queue is able to absorb it and still keep the same ultra-low latency on any operation you execute against this queue. So this is actually no joke. Like the Amazon.com website uses SQS queues as part of order processing, and it is a key component of building scalable and highly available services. And you typically don't use SQS queues on their own. Instead, when you think about your software architecture of your microservices, you think about what we call the pipes and filters, where you can combine SQS with a service like Amazon SNS, which supports pub subtopics. So a source of messages goes through an SNS topic, can get fanned out to multiple SQS destinations. You can apply filters when a fan-out happens, and you can hook up different systems processing copies of the message and reacting to events in your architecture. And SQS comes in with a rich set of integrations of systems that are able to send messages to an SQS queue. It's actually more than this short list, because there's a lot more services that integrate with Amazon Simple Notification Service, and connecting an SQS queue to an SNS topic is one of the easiest and most common things to do. So these are the producer integration systems in AWS that can automatically send messages to an SQS queue. Now, when it comes to consuming messages from Amazon SQS, the list is actually way shorter. Since Elastic Beanstalk was launched, There's a specific type of a beanstalk node called a worker node, which can come provisioned with an SQS queue. These worker nodes can go through a backlog of tasks served from an SQS queue and come with a nice on-box daemon implementation that pulls messages from an SQS queue and invokes HTTP requests on your own code. But that's not serverless. That's an actual node you end up provisioning in AWS Beanstalk as a worker node. And now the latest integration that we have on the consumer side is the integration with AWS Lambda, the serverless compute offering that we have. What's AWS Lambda? Well, you probably already know that. It's a very nifty service where you can write a small chunk of code, wrap it up, upload it to Lambda, and ask Lambda to execute the code for you based on provided input. And you as a customer, you don't have to think about servers or updating the operating system. Lambda is responsible for provisioning a worker instance on which your code will run isolated from other workloads. And what's interesting about Lambda is it actually supports 3 types of integrations of how you end up invoking your Lambda functions. There's a synchronous push model, which you can use basically by invoking Lambda functions synchronously. And in that model, you end up waiting for the response from Lambda, and you can actually learn what the outcome of the Lambda was. There's an asynchronous push model, which allows you to submit an invocation to your Lambda function. But you don't get to learn about the outcome of that operation. And that is supported by integrations with Amazon S3 and Amazon SNS. And the third model is more of an active pooling model where the Lambda team created their own integrations with event source services like DynamoDB streams and Amazon Kinesis data streams, and recently launched Amazon SQS, where you point your AWS Lambda to that event source, and the Lambda service is responsible for provisioning and auto-scaling a fleet of workers that end up pulling the records, rows, and messages from those data sources. And when you look at the scope of existing integrations with AWS Lambda, it's a long list of services. Basically, because Lambda gives you this flexibility of executing any custom code in an easy way, it tends to be super useful for most of the services to have an integration point with Lambda to either notify Lambda that something happened or even ask Lambda or for the output for some filtering or processing function. So those are the basics. We're going to talk about the 2 services today. And since Lambda launched integration with SQS as an event source, we can get to the topic of serverless message processing. SQS is a serverless queue. Lambda is a serverless compute offering. So let's look at the high level of how it actually works. We've got an SQS queue. We've got the Lambda service, and we've got the customer-provided Lambda function. So the story begins when a message is inserted into the queue and is stored durably in SQS. So SQS has this nice property that any message sent to SQS is replicated across multiple availability zones for high durability, which means that like once your send was acknowledged, the message is there to stay. So what happens next is AWS Lambda pulls the queue and fetches the available message and then passes it over to your own Lambda function as input to execute it. And then your Lambda function can do whatever processing it needs to do, possibly calling other dependent services to complete the processing of that message. Now notice on this diagram that even though Lambda already got the input and your Lambda function is working on the message still remains in the source SQS queue. And the reason for that is, again, durability and at least once message processing. What can happen is What if the Lambda function fails? We don't want to lose the message that was not fully processed. Instead, it stays in the queue, and once your Lambda function completes successfully, the Lambda service removes the message from the queue and consider it fully processed. So to bring it all together, it's a very simple diagram. The key to remember is messages stored in SQS are stored durably, and they are removed only after they were successfully processed by your Lambda function. And you can actually notice that there already is a similar integration or similar mode of Lambda, which is the async push we talked about previously, where you can submit some work item to Lambda, and it's going to be processed asynchronously, similar to like a poller working on SQS. So let's do a direct comparison of the features of just using the AWS Lambda asynchronous push versus combining an SQS queue and an AWS Lambda queue poller. Okay, so let's go side by side and compare. The async invoke is simpler. You just integrate it directly, and you only deal with your Lambda function. So it's kind of easier to understand, and you're only dealing with a simple resource. Whereas when you combine SQS and AWS Lambda, you're dealing now with two resources. So there's a little bit extra complexity in your architecture diagram. Both approaches give you automatic scaling. That's a given in both approaches, so there's no difference there. The async invoke allows you to works on individual invocations at a time, and the added benefit of combining an SQS queue with an AWS Lambda is in this mode it actually supports batching, which can reduce your cost or increase your processing speed. Your Lambda can get invoked with a whole batch of up to 10 messages to process at a time. Another difference is the async invoke supports only a simple dead letter queue policy. What's a dead letter queue policy? Well, imagine the message or invocation you're attempting to run on Lambda has some problem in it. Maybe the message is actually invalid. The system that sent the message or invocation provided wrong arguments. Or maybe your Lambda function has a callback, and for that one particular message keeps throwing an exception and fails to process it. With a Lambda async invoke, the message will be retried up to 2 times, so three times in total, and you can configure a DLQ destination, and after those 3 attempts the message can be moved over there. If you didn't configure a DLQ destination, then the message that failed twice in the async invoke will just be removed and dropped. Whereas when you combine SQS and Lambda, you have access to a more rich DLQ policy that is provided by Amazon SQS, where you can customize the number of attempts. And also, and that's actually a very interesting feature, that if you don't configure a DLQ policy, the message will never be removed from the SQS queue. It's going to be attempted to be processed again and again and again until the message expires. What does it mean that the message will expire? Where SQS queues, you configure them with a retention period. For each SQS queue, you can say messages that are sent to this queue should just disappear after X amount of minutes or days. The default is 4 days, the max is 14 days. So it's up to you as a developer to choose whether your Lambda should keep polling from SQS queue and keep retrying forever, or after X attempts, 5 or 10 or 20, the message should be moved to a separate DLQ, where then you can inspect it and fix your code and redrive the message to process it again. Another key difference is when you use a Lambda async invoke, the message gets processed eventually. It's processed asynchronously, but you have no visibility into what is the size of the backlog of async invokes for a particular function. You just submit it, and that's it. There are no specific metrics to tell you that there's 1,000 invocations pending or 1,000,000 of them. Whereas when you combine SQS and Lambda, you can actually benefit from Amazon SQS queues emitting metrics to CloudWatch, which give you visibility into the backlog size of your queue and also the age of the oldest message. So this is a very cool feature for monitoring your asynchronous processing, being able to see how far behind the queue is and react and alarm on these metrics. So basically it comes down to that on the async invoke side, you don't get any extra queue features, whereas in SQS you have access to all the SQS features, and we're going to look at them in the next slide in a second, what extra features you get from SQS by combining with Lambda. And there's one extra difference. The async invoke path, there's no extra cost. You just pay for the normal price for invoking a Lambda function. Whereas when you combine SQS and AWS Lambda, there will be this added cost of requests made to SQS. So even though Lambda behind the scenes runs a fleet of pollers polling from your SQS queues, you end up paying only for the requests made against the SQS queue. And for typical use cases, if your queue is not idle, there are actually messages going through it, the cost of attaching SQS to Lambda becomes a fraction of the cost of the actual Lambda usage, so it doesn't change your bill that much. All right, so let's look at all the other SQS features that you get by kind of for free combining it with Lambda. We talked about the DLQ policy, we talked about batching. SQS also supports delayed messages, and it's a very cool feature where when sending a message to the SQS queue, you can ask SQS to delay the message up to 15 minutes for processing. And you can imagine that if you're dealing with some kind of a legacy system that needs a few seconds, maybe a few minutes to catch up on like the state of the world before you can process the message, you just change the setting on the SQS and your messages get buffered and dispatched with a delay. You also have access to built-in server-side encryption with customer managed keys, which is a requirement in some of the enterprises and customers we talk with. You can configure a custom retention period. Like I said, it's by default 4 days, can go up to 14 days. You're in control of that. For systems that always want to go through every single message to process it, I recommend increasing it to 14 days. That gives you time, if you have a bug in your code, to go back and inspect the message, fix the code, deploy it, and the message will get processed. There's a different use case here where you have messages that are more volatile and they kind of have meaning for the next 5 or 10 minutes, but if they are older than that, you're not even interested in them and they can be safely dropped. And then you would go with a very short retention period and the queue would basically get rid of messages that are too old for you to process. We talked about the availability of CloudWatch metrics for the queue, and there's one extra feature in SQS, rarely used, but it's nice to have it there, which is the ability to purge the entire queue. There are certain cases where your system running in production may have an operational issue and you've accumulated a huge backlog and you want to recover. You actually want to make a decision instead of waiting for the system for multiple hours to go through the backlog to catch up and recover. You would prefer to just drop the entire backlog of messages and start with a fresh empty queue, and you can do it with a single operation on an SQS queue. Okay, so that's the high-level view of what extra benefits you get by combining AWS Lambda with Amazon SQS. Now, let's look at the internals of how the receiving process in SQS works and how does the AWS Lambda SQS poller work internally, and we'll learn through this experience about some of the settings we have to keep in mind when working with both solutions combined. So let's start by looking at how messages are consumed from Amazon SQS. So here we see a queue. with some messages inside. The messages in Amazon SQS standard queues are mostly ordered. There is no guaranteed order of messages. It's more of a bag of messages with some order that stems from the order in which you sent it to it. And on the right-hand side, we see 3 services that want to consume messages from SQS. So the way consuming works is these consumers just call receive message on an Amazon SQS queue. And they get to provide from which queue they want to receive messages, but they cannot tell SQS which message they want to receive. It's up to SQS to pick a message to return. So the first consumer calls receive message, and Amazon SQS sends the message back to this consumer. It decided to return this particular message. And what happens is, remember how I told you that the message is not removed from SQS upon receive? And this is exactly what happens here. The message remains in the queue, but becomes hidden for a configured visibility timeout. And the consumer gets the copy of the message and has now the opportunity to work on that message. While the message is hidden in the queue for a configured visibility timeout, no other consumer will get a copy of that message. It's kind of locked in the queue. So let's say another consumer called receive message, and again, it's SQS deciding which message now to return. It picks this one, returns the copy to the consumer, and 2 consumers are now working on messages. 2 messages are invisible. What happens when the first consumer finishes the processing successfully? Well, he's done with the message. What he needs to do now is delete message from SQS, getting rid of that copy. He is done with the message. Only then he confirms with SQS it's okay to remove that message, and the message is gone. What happens if the second consumer has some kind of a bug or the message is malformed? Well, an exception is thrown. He fails to process the message. He doesn't need to do anything else. After the configured visibility timeout, the message will become visible again, and another consumer can pick it up. Now, if you look at this closely, you already see this nice property of Amazon SQS, which is if you have a problem processing a particular message, that doesn't block you from consuming any other message from SQS. It's Amazon SQS that keeps track of which messages are being worked on, which were deleted, and keeps serving you available messages. So a problem with a particular message never stops you from processing other messages from Amazon SQS. And let's visualize to build like a good mental model of how it works, how a visibility timeout for a particular message works. It's actually pretty simple. The moment the message is returned as part of receive message request, SQS keeps counting the visibility timeout, and the other receive messages requests arriving while the timer is counting do not return this particular message. And after the timeout expires, another receive request can actually return the message again. If you're an advanced SQS user, you can actually use an API call called change visibility, change message visibility, and provide a custom visibility timeout for the message you're working on. So for some advanced cases where if you fail to process a message, you can call change message visibility and provide a timeout of 0, making it immediately visible to other consumers to retry processing that message. Or if you need more time to process the message, you can call change message visibility and extend the visibility timeout because you just need more time. So that's how it works in SQS, and that's how every code that integrates with SQS needs to work to consume messages from SQS. Keep calling receive message, and then after successful processing, call delete. So let's look at how a Lambda SQS pollers work. Well, they have to follow the same model of working with an SQS queue. So here we see a queue. Someone sends message to that queue, and on the right-hand side we see the AWS Lambda SQS poller. It keeps invoking long poll receives, which save a lot of cost of requests going to SQS, and is requesting batches. So in this particular case, only one message was sent. The batch contains one message. The SQS poller gets a copy of that message and invokes your function. Now, what happens when there's a sudden burst in messages coming into SQS queue? Another nice property of the Lambda SQS worker kicks in, which is it auto-scales the poller fleet. So what's going to happen in that situation is it's going to notice that there are more messages to process and provision automatically for you more pollers fetching messages from SQS, and behind the scenes, more Lambda workers invoking your function will be provisioned. Okay, so when the Lambda SQS poller invokes a Lambda function, things can sometimes go wrong. The Lambda function can fail, or maybe even you will get a throttling response because the sudden burst in traffic was more than the currently available Lambda worker nodes. So what happens in that situation? If we attempted, we have a message batch, we attempted to invoke the Lambda function, but the SQS poller in Lambda got throttled. Well, so the poller is actually smart, and it keeps track of how much visibility timeout is still remaining for that particular message. So it does a very simple operation of comparing of how much time do we have left with the configured visibility timeout versus what is the function timeout on the Lambda side. And if it's more, then we're just going to retry to a different Lambda function. What that means for you is message received from SQS once can be attempted by the SQS Lambda poller to invoke a Lambda function multiple times. And one of the recommendations because of that is if when you configure visibility timeout for the queue, configure it to be 5 or 6 times as much as your Lambda function timeout, just so you can give this mechanism an opportunity to retry to a different Lambda function. And that is key. It's actually mentioned in the documentation as a recommendation to configuring the visibility timeout with SQS to Lambda integration. There's a mechanism of auto-scaling here. We just saw how more workers were added to deal with the sudden burst in traffic. A similar mechanism works to reduce the number of pollers once the queue is consumed and no messages are available. So continuing this particular example, if that particular message batch failed on a particular Lambda invocation or got throttled multiple times, the visibility timeout would expire, and a message becomes visible in the queue again, and the second time it gets received, you can actually see in the details of that message that it's the second attempt. The receive count gets increased by 1, and this is how you can notice that, like, the SQS Lambda poller fetched the message from SQS, so you do have visibility into that. Okay, let's switch into a demo. I've pre-recorded a demo to avoid unexpected situations. And I'm going to explain as to what happens in the demo. We'll see this particular integration, and we start with going to the SQS console to create a new queue. We're going to call it webinar demo SQS. The region is Canada because I'm in Canada. We're creating a standard queue, and let's go and configure some advanced settings on this queue. So the key setting here is the visibility timeout, and because we will experiment with different length of Lambda functions, I'll set it here to 5 minutes. You can also configure other settings like the mentioned retention period of messages, the max message size, the delivery delay if you want to have delayed processing of messages, This setting enables long polling on the queue, so by default, long polling is better and cheaper. The advanced settings for the DLQ policy, and the server-side encryption with customer master key. Okay, single click, queue exists, and we can see there are no messages in it as expected. We just created it. Let's switch to the Lambda console and create our Lambda function. We're going to create this from scratch. Let's call it webinar demo Lambda. We're going to use Node.js and JavaScript to write some simple function, and I've pre-configured a role which this Lambda function will use to run. Let's create it. Okay, so here's our Lambda function. And let's start by, on the left-hand side in this nice console, you can see the list of triggers available to quickly hook up to invoke your Lambda. But let's first look at the actual Lambda code. This is the default template for Node.js, and actually I prepared a little bit different handler to deal with messages coming from SQS. So we can see a helper function to do a sleep for a configured millisecond time here, and this is the handler that gets invoked for every batch of messages coming in. So how do you know what is available in this thing? It's actually documented. When you go to the AWS documentation, you see examples of messages and inputs for different events. So this is an example of a batch of messages coming in from SQS, so what you should expect. So what we're going to do is we'll just record the number of messages in the batch, output it to the console, sleep for 100 milliseconds, and then output that we're done. And there's one extra thing we need to do for our newly created Lambda function, and that is configure the timeout for the function to run. I'll set it to a minute because we'll play around with different delays in that Lambda to see the behavior of queue processing. So 1 minute should be enough for us. Okay, let's save these settings and let's see how this code behaves by sending invoking in with a test input. There's a nice template for events coming in from SQS. Let's call it test SQS, and you can see that it's going to be a batch of just one message received from SQS. So let's create that test input and let's test our Lambda. All right, so Lambda got invoked. And here we can see the output, how it saw one message as expected, how we ended up waiting 100 milliseconds, and then we said done. Okay, so it works correctly. So the next thing we're going to do is connect our newly created SQS queue as the event source for this Lambda. And it's easy. We just point it to the newly created queue, configure the batch size, and enable the integration. All right, click Save, and immediately a Lambda SQS poller got created and started calling receive message on the queue. So if you go here and refresh, well, nothing has really changed because the queue was empty, so nothing got received. But I've prepared a small program that can send messages to an SQS queue in a loop. So let's start multiple copies, and it's just a simple program that sends message in a loop and increases a counter. So with 5 copies, we'll generate some traffic of messages going into SQS, so we can see how it performs and auto scales. All right, so this is the 5th application sending. All right, and yeah, so there's around 20 messages per second being sent, maybe more. Let's refresh it and immediately see that messages in flight means messages received but not yet deleted, that the Lambda SQS poller is actually picking up those messages, invoking our Lambda and processing them. There's no backlog being built because our Lambda is fast. It takes only 100 milliseconds, and it got auto-scaled to support this number of messages. Looking at the measures here, we can actually see some of the data coming in from our Lambda polling messages. Okay. So what we're going to do now is, obviously this with this configuration, our Lambda was keeping up with the incoming rate. But if we change our code now to spend 10 seconds processing the message, it now means that suddenly our Lambda is much slower and there's a backlog in the queue. We keep sending messages at the same rate, they keep arriving, and SQS absorbs them. And at the same time, the auto-scaling behavior of the Lambda SQS poller kicks in, and it creates more and more nodes polling from SQS and creates more and more Lambdas running concurrently. Let's confirm what happens here by going to CloudWatch logs for our Lambda. And we see a few of the freshly created Lambda instances just because they had to be auto-scaled. They don't even have any entries about successful completions. Oh, here's one that got a full batch of 10 messages. Here's another one that just got a batch and is still waiting for the 10 seconds. And here's one that just got created by the Lambda poller. So going back here, we can see that the number of messages in flight keeps increasing as the Lambda SQS poller keeps scaling up, adding more pollers, invoking more Lambdas concurrently. And at some point, this auto-scaling mechanism will catch up in a few seconds. And we'll see the backlog of messages in the queue dropping to 0 because it auto-scaled exactly to the rate of incoming messages. So let's keep refreshing. We can see that the number of messages in flight keeps increasing and the backlog keeps dropping. So the messages are still coming at the same rate. It's just the auto-scaling behavior of the Lambda SQS poller that allowed it to catch up. Switching back to the metrics, we can confirm that, yeah, our Lambda is working 100% available, no functions are failing, it's a lot of invocations. Okay, so in this demo we saw how easy it is to configure an SQS queue as a source for Lambda invocations and how Lambda auto-scales its behavior to match the rate of incoming requests. So let's talk about one extra advanced topic here, which is limiting concurrency for Lambda functions. Let's go back to our example, the simple high-level example of of a Lambda function that is connected to an SQS queue, and it does something. It calls maybe some dependencies, and we just saw how the Lambda SQS poller can auto-scale to handle with the incoming traffic, spinning up more and more Lambda functions concurrently. Now, imagine that this system, that Lambda function, is talking to something that actually has a limit. Maybe it's directly talking to something like a relational database that has a limitation on the maximum amount of open connections to the database. Or you're talking to a service that behind the scenes is talking to a relational database that has certain scaling limitations. In that situation, you will actually potentially run into a problem. If there's a sudden burst of traffic going into the input SQS queue and the Lambda poller scales up to deal with this incoming rate, your Lambda function calling that limited dependency would start browning it out. It would cause an overload of that limited capacity downstream dependency. So in those situations, what you actually want to have is you want to be able to limit the concurrency. You want to be able to limit the number of Lambda functions that are allowed to run at any given point in time. And basically when your incoming traffic exceeds a certain threshold, it's supposed to be capped. Imagine your RDS database is configured to accept only 50 connections. You can limit your Lambda concurrency to 50, preventing it from attempting to establish extra connections and failing. So when talking about concurrency limit, there are actually two settings available in AWS Lambda. There's a limit per account that is shared across all the functions that don't have a limit, or you can be very specific and set a limit on a specific function. The recommendation is to actually think about the concurrency limit and set it for every single Lambda function. Why is that? because you want to avoid surprises in your production system. Imagine you have 10 Lambda functions and none of them have a specific function limit. They just all use the shared account limit of concurrent invocations. And they all happily churn along and run. And then suddenly there's an increase in invocations to one of those 10 functions. And because they all use the shared account limit, this actually leaves less available concurrency invocations for the remaining functions. So one function having a lot of concurrent invocations can cause other functions that are maybe not even related to start failing for you because there's no more capacity available. So think about it, and my recommendation is to always set a concurrency limit for each Lambda function to avoid these surprises of one function kind of stealing capacity from a different function. So let's see how this behaves in a second demo. So we're going back to the same situation we just left, where we've got the 5 producers sending messages. The Lambda is taking 10 seconds to process a batch of messages. It's been running for some time, so you can see the metrics on the queue reported and accumulated. And yeah, behind the scenes here, we can see that the 5 applications are still sending messages to SQS. So let's switch to the Lambda console. And in configuration, right down below, there's the concurrency setting. So for our example of Lambdas processing 10 messages for 10 seconds, we now say there's a limit and only 10 of these can run at a time. Okay, so we just set this concurrency limit, and let's see the behavior of the SQS poller. Immediately we see that again, a backlog is being created on the SQS queue, and the number of concurrent messages we're working with keeps going down. The Lambda SQS poller sees the back pressure from the concurrency limit on Lambda function and has to step back and slow down the consumption. So this triggers the scale down behavior of the AWS SQS poller to match the concurrency limit. And for a while, we'll see that this messages in flight is not exactly 100, which is the expected what we would see when we have 10 Lambda messages processing batches of 10 messages. What is going to be very approximate, and at some point is actually going to stabilize at this rate of processing. And yes, as expected, we set the concurrency limit on the Lambda to 10, so Lambda started throttling invocations. We see the metric of throttles appearing and the SQS poller reacting to these throttles. All right, so number of messages currently in flight, so messages we're working on, kind of stabilized on the number of 60, and the SQS Lambda poller keeps scaling down, and at some point, as the throttles stop appearing because the it's not bombarding this at a high rate, it's going to stabilize. And here we see a particular Lambda processing batches of 2 or 10 messages. Okay, so we're approaching a stable state. We can simulate that the burst of incoming traffic just stopped by stopping our message senders. And what we're going to observe is with the concurrency limit of 10, the Lambda poller will at its own rate consume the backlog of messages, and the number of messages available in the queue keeps dropping as we slowly consume through the backlog after the processing rate stabilized. Yeah, so at this point, messages in flight is 98. The size of the poller fleet matches the concurrency limit on Lambda, and that's how you can protect downstream resources from being overloaded by multiple Lambdas, like too many Lambdas talking to your dependency at the same time. Okay, so let's recap what we've talked about today. SQS and Lambda are better together. You get full features of SQS queues with the nice serverless compute power of AWS Lambda. It's basically peanut butter and jam of the serverless toast. They just go nicely together. When you work with both services, mind the timeouts. Mind the timeout of the Lambda function execution, and mind the visibility timeout, which is supposed to be 5 or 6 times larger on the side of SQS to allow the Lambda SQS poller to retry. And remember about controlling the concurrency of your Lambda functions to protect your downstream dependencies, if there are any that would suffer from increased load, or just to be just to have an expected allocation of resources in case one of your Lambda functions bursts. All right, so that's it, but I actually have a few extra slides that I want to talk about. One of the event sources for Lambda is also Kinesis data streams. So let's compare the two event sources, SQS and Kinesis, and how they differ. So remember when we looked at the way messages are consumed from SQS, that SQS keeps track of which messages are invisible, which are done, and we never have a case where a failure to process a message blocks processing from other messages. So let's compare it directly to how Kinesis data streams behave when connected with Lambda. Kinesis data streams are built from multiple shards, and a shard is an ordered stream of records. What's different here is that it's on the stream reader to keep track of how far they are reading a particular shard. Specifically, when you hook up Lambda processing on a Kinesis data stream, you will end up with a single Lambda function for every shard in the Kinesis data stream. And if things work correctly, your consumption can move forward. But what happens if you find a message that you cannot process? There is no DLQ mechanism here. Your consumption for a Kinesis data stream will stop, and until you actually successfully process a particular item. And if you do, only then you get access to more records sitting behind in that backlog. So it's also a viable solution for serverless message processing, as long as you're aware of this key difference of how a failure to process a single entry affects the availability of your entire service and processing of further messages. All right, so that's it for everything that I've prepared for today. Hopefully it was you found it all useful. Thanks everyone.